Well, hi there. Good to be with you again today. I was super excited to introduce the concept of an antiderivative to you yesterday, and we're going to continue working with those antiderivatives again today. And we're going to connect those to the integrals that we were working on. So this is called the fundamental theorem of calculus, the antiderivative part of that. And so it's the connection between the idea of an integral and what it represents and the idea of an antiderivative and how to compute it, how to calculate it. So remember, when we introduced the idea of an integral, we said that that symbol represents area. And the area is written very elegantly with the integral notation from a to b. So how do you figure out the answer to an integral? So number one, we saw that you could do the geometry. Since it just represents area, if it's a recognizable area, then by far the easiest way is to simply do the geometry. Okay, that's going to be faster than any calculus that you'll do. Our second way is today, where we're going to see how an antiderivative evaluates that integral. And then number three, we're going to save for Thursday together. So this is the fundamental theorem of calculus. It connects the idea of the integral to the idea of the antiderivative. It applies to a function that is continuous. It has to be continuous within its interval from a to b. Okay, once you've established that it's continuous, then you can apply this theorem. So the integral from a to b of the function f of x with respect to x is equal to the antiderivative, so capital F of x, plus the constant c, and then we write a and b here at the end of our brackets. And then what we do with our a and our b is we plug them into the antiderivative. So we take b and we plug it in. So we're going to have the expression f with the antiderivative of f with b plugged in plus c. And then we also will plug a in. And we'll have the antiderivative with a plugged in plus the value of c. And we subtract those two together. And the difference between them is equal to the area that you would get with geometry, or this is what we do when we can't do geometry. Okay, this is the part where the Greeks failed. Once it got beyond geometry, they couldn't do it. So once we got to Newton and Leibniz, and we had the development of the antiderivative, now they could find the antiderivative under curved things, so trig functions, logarithm functions, square roots, using this idea of the antiderivative. So it's such a cool thing to see that any integral of any continuous function can be calculated without limits, without rectangles, without effort, as long as you can do an antiderivative. So any integral, any continuous function, and we don't need limits, we don't need geometry, we don't need rectangles, we don't need a whole lot of effort as long as you can do the antiderivative. Okay, this is just it's really just phenomenal. It's such a powerful theorem. It's the culmination of everything we've been working towards. So here is the example of a parabola. It's a parabola of 3x squared plus 1. We want to go from -1 to 3. And so we will use the concept, because it's curved, we can't do geometry, so we'll use the concept of an antiderivative. So in a bracket, we're going to put the antiderivative 3x squared, which is x cubed, plus the antiderivative of 1, which is the value x, plus the constant c, evaluated starting at -1 and ending at 3. And now we'll substitute our bounds. So I'm going to have 3 squared, cubed, plus 3 plus c, minus, and I'll put -1 in, -3 cubed, plus -1 plus c. And we'll evaluate what we get here. So that's 27 plus 3 plus c minus -1 minus 1 plus c. So we're looking at 30 plus c plus 2 minus c. Did you catch that I distributed my negative here? So I get 32. So let's connect that to the visual. So the visual of this is that we've got a parabola, 3x squared, and going from -1 to 3, that 32 represents the value of the area bounded underneath the curve and above the x-axis. So that value here is 32. Let's do a trig one. Let's evaluate this using the antiderivative. Okay, so in our brackets, we do the antiderivative of the sine of 2x. So the antiderivative of sine is negative cosine. Leave the inside alone. Now normally with a derivative, we would have multiplied by the chain rule. But in an antiderivative, we have to divide by the chain rule, so I divide by 2. Plus the constant c, going from the bound of pi fourths to the bound of pi halves. So now we'll substitute in. We've got negative cosine over 2. I'm going to write negative 1/2 of the cosine of 2 times pi halves plugged in, plus the value of constant c, minus negative 1/2 times the cosine of 2 times pi fourths, plus c, and my parentheses. So that's negative 1/2 of the cosine of pi plus c, and then plus, I'm distributing my negative, 1/2 of the cosine of pi halves minus c. Now the cosine of pi is -1, so negative 1/2 times -1. The positive c and the negative c cancel each other out. And then 1/2 times the cosine of pi halves, which is 0, so we're looking at 1/2. So the visual representation of this, we are looking at a sine graph because of the period of this sine graph. We know that pi is out here, which means we've got pi halves in the center of the rotation of the cycle, and pi fourths. So the visual representation is that the area bounded between the curve and the x-axis, that will have a value of 1/2. Let's do an exponential function using an antiderivative. So the antiderivative of 3 to the x is 3 to the x itself, and normally we would normally we would multiply when we're doing derivative rules, so this time we divide by the ln of 3 and the chain rule of 1, so plus the constant c, going from 1 to 4. And then we'll substitute our upper bound of 4 in, so that's 3 to the 4th over the natural log of 3 plus c minus 3 to the 1st over the natural log of 3 plus c. So that's 81 over the natural log of 3 plus c minus 3 over the natural log of 3 minus c. And those two cancel each other out, so we're looking at 81 over the natural log of 3 minus 3 over the natural log of 3. In other words, 78 over the natural log of 3. And that's an exact answer. I don't want a decimal. Okay, I just want the exact answer. And so connecting that to the visual representation, We know that an exponential function hugs the x-axis, swoops up through the number 1, and then continues up, and we are going from 1 to 4. And so the area bounded beneath the exponential curve and above the x-axis has an irrational value. It's exact, but it's irrational. Okay, so I can come up with an exact value of 78 over ln 3, but it is an irrational number. So this will be 78 over ln 3. Here's another exponential graph. This is e to the half x. So the antiderivative of e to the half x is e to the half x divided by the ln of e and the chain rule of 1/2 plus the constant c going from 2 to 7. Now we know the ln of e is 1, and it's awkward to divide by that fraction, so it's probably better off if we write 2e to the half x plus c from 2 to 7. So that'll be 2e to the 7/2 x plus c minus 2e to the, the 7/2, not 7/2 x, to the 7/2, and then 2e to the first plus c. We distribute the negative, and so we end up with 2e to the 7/2 minus 2e. Okay, that can't be simplified. It could be factored, perhaps. You could take out a 2e. That would leave me with e to the 5/2 minus 1. But either way, again, it's an irrational but exact number. And so you could express that with your visual representation. So e to the half x is an exponential function that comes down and decreases. And when we're going from 2 to 7, we're looking at this small amount of area bounded between the function and the curve. And then we've got our irrational but exact answer of 2e to the 7/2 minus 2e. Okay, let's look at this hyperbola, 1 over 2x minus 1. This is a hyperbola that's been moved, shifted to the right with an asymptote at 1/2. So maybe think of your visual representation maybe first. Okay, a hyperbola, it has an asymptote at 1/2 because of the domain, and then this has been moved. Okay, so you have your hyperbola here, and then you've got the other branch of your hyperbola. And we're going from 4 to 7, so that's 1/2. So 1, 2, 3, 4, and then 5, 6, 7. So we're looking at this little teeny wedge of an area under that hyperbola. Okay, so let's do the antiderivative. Okay, this is an antiderivative that has x in the denominator, not x squared. And so this is an antiderivative that's going to require a natural log. So this is the natural log, which requires an absolute value of 2x minus 1. And it also requires division by the chain rule. So we're going to divide this by 2. And you can check it by taking the derivative again, just to make sure you didn't make a mistake. Plus the constant c from 4 to 7. So this would be the natural log of the absolute value of 13, after I plug in 7 over 2, plus c, minus the natural log of the absolute value of 7 over 2, plus c. All right, so distribute the subtraction, cancel out the c's. So I have the natural log of 13. Now I don't need the absolute value because 13 is a positive number, over 2, minus the natural log of 7 over 2, which also could be written as 1/2 times the natural log of 13 minus the natural log of 7. And natural log subtraction could also be written as the quotient 13 over 7. So that irrational number is the exact value of the area under the visual, under the graph. All right, you recognize this crazy equation? Okay, it's a negative, and it's got that absolute value in the square root, so hopefully you recognize that as being the derivative of the inverse cosecant graph. So this would be the inverse cosecant of x plus c going from 2 to 2 over rad 3. So this will be evaluated as the inverse cosecant of 2 over rad 3 plus the constant c minus the inverse cosecant of 2 also plus c. All right, so distribute or subtraction. So the c's each cancel out. All right, now to evaluate this, when I'm doing inverse trig, I always switch it to its companion, to its reciprocal. So cosecant inverse could switch to sine inverse, and then I can deal with rad 3 over 2. And then minus cosecant inverse can turn to sine inverse, and I can look at half. So the sine inverse of rad 3 over 2 is pi thirds, and the sine inverse of 1/2 is pi sixths. So we're looking at pi thirds minus pi sixths, which is pi sixths. And that again represents the irrational but exact answer to the area under the curve if we would draw it visually. All right, so that took less than 20 minutes. Not a big deal, but it's like the biggest idea, the biggest thing of all of second semester is the connection of the idea of an integral being evaluated not just with geometry, but making the leap now to using the antiderivative to evaluate an integral. So don't deny it. You might just have a little bit of fun working on this homework. And then we'll come together on Thursday and we'll talk about the third method that we could use to evaluate an integral. All right, see you then.